Great. So today I'm gonna be annotating and analyzing the rest of this scientific paper, and then I may jump back and forth to my art homework just for breaks, but we'll see. And I'm wondering if this may help me kind of explain it to myself if I'm recording like I'm trying to explain it to someone else. So far, um, this is a paper by my professor, Gagik Melikyan, on the radical reactions of 1,4-alkadienes, metal coordination as an effective tool for controlling the regio and stereoselectivity of the CC bond formation. So the synopsis says that, maybe on this screen, I wonder if I can make it bigger. Okay. Um, so this experiment found a novel method for selective generation of radicals in 1,4-alkadienes by employing a pi-bonded cobalt CO6 core, carbon dioxide core, as a triple bond immobilizing cation stabilizing and radical guiding auxiliary group. So if you see here, we can see that pi-bonded core that is stabilizing the 3 alkadienes on the ends. I mean, 4. So this occurred in a regio and stereoselective manner, giving rise to tetrathienolethanes. Uh, so that's what we see with the formation of DL diastereomers, 82 to 93%. Okay. Easy access to tetraethylenoletanes. Novel phenomenon of chiralization by metal complexation. Highly reductive complexation of the acetylenic groups. So I don't know if the intent was to form this molecule, but I think the intent was to figure out how these reactants would react with the acetylenes, and they formed a stabilizing. It probably, I mean, obviously these experiments are created with intention, so it seems like this was a very successful experiment, and they achieved the intention of stabilizing the acetylenic groups. So this could be a very useful tool for us. Um, so I'll summarize what's going on. So radical reactions of 1,4-alkadienes are kind of not studied much because the free radical, as you can see right here, um, it makes it difficult to it's you want to introduce it into that position, but it's hard to do that. And a free radical is one electron. So usually electrons are in pairs, they're in twos, and two electrons make a bond, which is all the bonds you see between these atoms. But a radical is when it's just one electron, and then that one electron can combine with another electron, maybe another free radical, and they can create a bond. So this experiment is taking advantage of the free radical. So there was a lack of methods for selective introduction of an unpaired electron to the proper Gill position, and an intrinsic ability of the triple bonds to rearrange into isomeric allenes in both ionic and radical reactions. Allenes are just double bonds, so it would naturally rearrange into this thing over here, right here. This is an allene on the right over here, and they don't want that in this experiment. So it was hard to separate the head-to-head, head-to-tail, tail-to-tail dimers. Um, So they found over the past decade that a complexation of the triple bond with a dicobal hexacarbonyl group allowed for the avoidance of unwanted acetylene allene rearrangement right there. And so in this specific experiment, they report on radical reactions of 1,4-alkadienes in which one of the triple bonds is immobilized by the metal complexation in figure 1. Okay, so it's like this. This is like this. Um, it's immobilized, thus precluding an acetylene-allene rearrangement, restricting the reaction size to alpha, gamma, and gamma prime, and decreasing the number of regioisomers that could potentially be formed. And then sorry, I just woke up, so I think that's my voice is weird. Regioselectivity of zinc-induced dimerization reactions was studied to probe the relative reactivities of the propargyl radical, number 2. So I'm gonna write that number 1 triple bonds is immobilized by metal complexation. Triple bonds immobilized by metal complexation. And then over here, they're saying its Lenic counterpart. So the regioselectivity of zinc-induced dimerization reactions was studied to probe the relative reactivities of the propargyl radical, which is 1, and its Lenic counterpart. Lenic counterpart of propargyl radical, which is this one. I don't see the Lenic part because there's no double bond. Oh, I guess they're saying because of the resonance. Okay, whatever. 3 with an unpaired electron being located at the alpha and gamma to the metal core specifically. Okay, I see that. Um, so actually, I'm just gonna make that a highlight instead. And then we're talking about the alpha and gamma position. The unpaired electron is alpha and gamma to the metal core. Why do I feel like they're talking about 2? Oh well, I'm going with the numbers on the paper. So the requisite diacetylenic alcohols 4 and 5 were synthesized by condensation of ethyl formate. So let's go down here. So they took the acetylenes right on the left, and then using ethyl formate right here, they formed 4 and 5. Uh, they protonated it to become an alcohol that formed 2 resonance structures, and then zinc probably reduced it to form 2 other resonance structures with the radicals now. Okay, so I'm just gonna circle this guy. So those guys are newly introduced. And then it couldn't form tail-to-tail coupling or head-to-tail coupling, which I believe was desired, but it did form head-to-head coupling, forming the 1617 alpha-alpha dimer. And then with decarylization, it turned into that. And then you added phenyl groups for 28. Okay, so this is that structure. It's an X-ray structure. I was annotating this yesterday to kind of figure out how to see this. It's 3,4 DL. Dude, I'm not here yet, but I'm pretty sure that's nano. I don't know what N2 is. 3,4 bis trimethyl silyl ethanol 1,6 bis trimethyl silyl 1,5 hexadiene bis di cobalt hexacarbonyl. Okay, so I don't. Let's. All right. So right here in this paragraph on the right over here, they're just explaining the picture that we just found on here. And so I'll skip that because I already read that, had all the specifics. Uh, and then they're saying TLC wasn't super helpful or possible, I think, or NMR. So they used X-ray crystallography. And then that's why we got this structure up here because that's an X-ray structure. And then they were saying that they put the bulky TMS groups gouache to each other. So gouache is like this. Um, Gouache is like this. Say there's a substituent over there. Gouache is putting the other substituent right here so that they're kind of close to each other, but they're not eclipsed. They're not on top of each other. So this is a molecule, and um this is called a Newman projection, I believe. And they're saying that TMS groups are positioned gouache to each other. TMS is in purple. I circled it in purple. Okay. So if you can see right here, those guys are definitely gouache. Those are like almost next to each other. And then they're saying the cobalt are anti to each other, and we can see that. So anti is like this. So they're completely 180 degrees from each other. So you can see that right here. Cobalt I circled in blue. So this is all to minimize steric hindrance. Okay. Minimizing repulsion. Focus were placed far apart. Okay, so I think I'm getting to the part where I haven't gotten to yet. So overall, the enhanced chemoselectivity also manifested itself in a higher isolated yield of diisomeric products. Okay, so let's start highlighting because this is untouched territory so far. Noteworthy that the stairs look to be the radical CC bomb formation, often levels higher in the TMS grouping. Present at the stability terminus. That's for another example of 1,3-steric induction by a remote and removable trimethylsilyl group. So the addition of the trimethyl group, silyl group was the TMS group was intentional and favorable. Favorable for stereoselectivity. So controlling the reaction basically. Oxidative decomplexation of DL with steric ammonium nitrate allowed for release of tetraene. Decompensation step accomplishes decarylization of radical dimers due to elimination of C3 and C4 stereocenters. Yellow and tentraene was isolated in good yield. Synthetic, versatile access to ethylene carbon frameworks, 5 steps. With a total yield of 17%. Oh, class organic compounds. The complication of something when it's getting higher. Okay. Triple bonds are not subject to complexation. Ooh, it's getting hot in here. Ooh. Human projection 31 represents the non-complex data. Projection 31. Okay. Predisposed to metal complexation. Resistant. Huh. These guys are resistant, while this one is predisposed. Interesting. Why? Let's go back and forth from this picture and the text. So, okay. So, oxidative decomplexation of DO16 with ceric ammonium nitrate allowed for release of tetraene. So, 16 to 26. So, oxidation of this oxidation allowed for that molecule. It looks like the reaction can't go the other way. And decomplexation means it definitely took off the metal groups. Release of tetraene, 80.5% from a metal bondage. Yeah. Four-step synthetic scheme in overall yield of 15.7%. Analogously, organic product 27 can be liberated from the diastomeric mixture with an overall yield of 31% over 4 steps. So unique literature protocols for 26 and 27 afforded the former in 3 steps in a 10.7 overall yield, with the latter synthesized also in 3 steps but lower yield. Okay. It's noteworthy that the decomplexion step also accomplishes decarylization of radical dimers due to the elimination of C3 and C4 stereocenters. Okay, so carylization step is right there. Decarylization step. I don't really see it. I think they're just letting us know. Okay. Um, so decalculation by decomplexation was not previously observed in conventional releases of pi-bonded organic ligands. Tetraene 27 was dehydrogenated at the C3, C4 position by DDQ. I don't think it's on here. Okay. Benzene anaerobic conditions, light sensitive, neon yellow, and triene was isolating good yield. 28 is not on here. Okay, so acal substrate. Okay, so when 626 tetraene was treated with cobalt, complexation of settlement substrate topology, two equivalents could form three isomeric bias complexes. So 26 to 29. Okay, yeah, right there. So two equivalents made 29. Geminal bias complexation. So it looks like we added a metal groups right there. And then all the equivalents will make the tetracomplexation. And then okay, monocomplex, three additional sites for medical regions. Let's see whether the spatial cost can be gouache. Impedes an incorporation of pi bonded metal core with an anti-alkyl. Okay, so gouache, it's because of the gouache positioning of the right here that it impedes incorporation of another metal core. So an X-ray structure, figure 2. Yep, right up there. Validates said interpretation with uncomplex triple bonds being positioned between two cobalt alkyne cores in the sterically congested area. 27 turned into 17. Yep, like this right here. When treated with 4 equivalents of CO2, reactions are preceded by selective complexation of stably into triple bonds. It's like the tools. Okay, conceptually, these reactions are preceded by selective complexation of sterically hindered triple bonds with transition metals. Okay, in an all-carbon environment, bicomplexation with dicobalt octocarbonyl occurred selectively at least hindered sites, symmetrical fashion without introducing chirality into the parent molecule. A highly region-steric selective bicomplexation of tetraenes has two synthetically important ramifications. Okay, here we go. First, the concept of chirization by metal complexation would allow for chirality to be introduced into an achiral molecule without compromising carbon framework of the substrate or forming any new sigma bonds. Then for targeted modifications in select parts of the molecule, those that would potentially benefit from newly acquired chirality, and at the final step for an easy removal of pi bonded metal cores, retrieval of original carbon framework. Second, introducing a triple bond into a constrained area of a molecule would make it unreactive toward metal coordination. New method for protecting acyclic moieties. Structural integrity of the functional group is preserved, while access of reagents to said functionality is restricted for steric reasons. Great. And then here are the references. And we're done.